All right, we are going to talk about polar coordinates. Now, we already talked about polar coordinates a little bit earlier this year, but we're going to take them just a little bit further in this section. So this is what we're going to be covering, and I will have all of this bookmarked once I finished recording and know the timing. But we're going to review polar coordinates, and this is pretty much what we had done previously. We're also going to look at how you describe an area on a polar graph. This is kind of a little preview of what we're going to need when we actually do calculus of polar graphs next section. We have looked at number 3 also a little bit, converting an equation from rectangular to polar, but we're going to review that again. And then we're going to look at sketching graphs. We'll look at sketching a graph in polar form, and then we'll end with some common graphs. So that's what's going to be in today's lesson. Let's take a look and see what we got. Okay, so just a quick reminder of what polar graphs are, or polar coordinates. So remember, we're used to rectangular coordinates where we have an x and a y coordinate, and the x tells us how far to go horizontally, and the y tells us how far to go vertically, and we have our points. So the point 2, 1, we go 2 units in the positive horizontal direction and 1 unit in the positive vertical direction. That gets us a point. 0, -3, we don't go anything horizontally, but we go -3 vertically, so on, like that. Polar coordinates, instead, they're given in the form r theta. So, for instance, if I had this point right here, which, if we take a look, we can see, if we assume that we're counting by ones on the axes, then we can see that this point lies on a circle with a radius of 2, so its r coordinate is 2, and we can see that it lies on the angle pi over 4, so we can call this guy 2 pi over 4. And this one right here, think about what that one would be for a second. And this one is on a radius, a circle with a radius of 3, but we're over on the angle of pi radians. Now, remember, we did talk about a negative radius. So this point that I first drew, I could have also made it -2 5 pi over 4. So it's on the ray at 5 pi over 4, but instead of going +2 units out from the origin, we're going -2 units out from the origin. So we go in the direction opposite of 5 pi over 4, and we still lie on that same point. So think about what the angle would be if I wanted to label the second point, but not with a +3, but with a radius of -3. And hopefully you were thinking an angle of 0, maybe 2 pi. Either one actually would have been okay. So if we could think of going out in this direction, but then we have to go negative, we wind up with these coordinates right here. So that's just kind of your brief reminder of that. We did look at these conversions between the two last time also. So remember, if you want to convert from polar to rectangular or rectangular to polar, these are the convenient equations you can use. So the x coordinate is the same thing as r cosine theta. Y coordinate is the same thing as r sine theta. We can also look at r as the square root of x squared plus y squared, Pythagorean theorem. And then tan theta is y over x. So those are the convenient equations we can use also. Okay, so let's take a look at converting. Now, because this is review, what I would actually encourage you guys to do is go ahead and pause the video, see what you get, and then come back and take a look at the answers. Okay, so let's take a look at the answers here. So we're converting these from rectangular to polar. So we're going to assume these are given in rectangular. So we have x, we have y, we want to know r and theta. We have our formulas from above. So remember, r is the square root of x squared plus y squared. So you could just use this. However, let me just work this out, and you get r equals 4. And then theta, we could use tan theta is y over x. So we have negative 4 over 0, so it's undefined. Oh no. But sometimes rather than just mindlessly going through the formulas, think about the picture. What would this actually look like? If we were to plot the point 0, negative 4, I'll just do it really quickly over here. 0, negative 4 is down here. Well, think about your r and your theta then. We can see very easily it's 4 units away from the origin, so r is 4. And then we can also see that that is on an angle of 3 pi over 2, which makes sense because the tangent of 3 pi over 2 is undefined. So sometimes you don't need to go through the formulas. You can just use what you already know. So I'm actually going to erase this, because don't always go mindlessly through the formulas. Just take a quick second to stop and think. Just remind ourselves though. So this is down here at the point 0, negative 4. So we can see that r is 4, theta is 3 pi over 2, because that's going to be theta. So the coordinates are 4, 3 pi over 2. Much easier that way. And if you can visualize it in your head, you don't even have to show any work. Okay, so then we think about b. b, again, let's just think about this. I mean, negative 2, that's going to be right there. And if we were to think about a triangle, we can see that that angle is going to be 5 pi over 4. And also, if you can use the Pythagorean theorem and find r, but if you know your special right triangles, you can also easily see that that's going to be 2 root 2. So r is 2 root 2. Theta is 5 pi over 4. And again, you're done. Very little work. Yay. All right, so I'm seeing a root 3. That's making me very suspicious. It's going to be a 30, 60, 90 triangle. Let's see if it is before we jump into anything. Let's see, it's going to be in quadrant 4. So this is 7 root 3, and this is negative 7. And my picture's not drawn to scale, but I can see that this leg is this leg, excuse me, multiplied by root 3. That is a special right triangle then. So this is the shorter leg, which means this angle is pi over 6. So I can see the theta that I'm looking at. I could call it negative pi over 6 or 11 pi over 6, either one. And my hypotenuse is going to be 14. So 14, I could say negative pi over 6. Again, just to kind of play with the different ways you can write the answer. So we have something like that. Now, negative 3, 5, all right, this one we're going to have to go ahead and do our formulas. So r is x squared plus y squared and a square root. So r is the square root of 34. And then tangent of theta is y over x. And if I do this on the calculator, so the tan inverse of negative 5/3, I'm getting about negative 1.030. Now, we do have to be careful. Let's think about this one. I'm going to move this over slightly. Think about which quadrant you're in. Oops. So negative 3, 5, we are actually in quadrant 2. That's negative 3, 5. However, this answer that we got for theta, where do you think this is? You should be thinking this is in quadrant 4. If you I mean, there's a couple of ways to get it. First of all, I mean, negative 1.030, that's not going to go enough to get you out of quadrant 4. So it's quadrant 4. Also, the range for tan inverse is quadrants 1 and 3. I'm sorry, quadrants 1 and 4. When this is positive, the tan inverse of this will be in quadrant 1. When this is negative, which it is, the tan inverse of this is going to be in quadrant 4. So this angle is in quadrant 4. We just need to add pi to get into quadrant 2. So you just have to be a little careful. And so if I add pi, I am about 2.111. So this point is at root 34, 2.111. So we had to do a little work and a little thinking on this. So there's converting from rectangular to polar. A lot of times we're working with convenient things, but if we have to fall back into the formulas, just be very careful with the tangent to make sure that you're actually in the correct quadrant. All right, so that's that way. What about the other way? So again, I encourage you guys just try these on your own first, but since you've seen it, you can check our answers together in a moment. Okay, so the thing that I notice on these, now remember these are starting in polar. So our angles, our theta, 0 is a very friendly angle. We know how to work with that. Pi is also very friendly. All right, pi over 8, maybe not so much. But 0 and pi, just think of the graph. So if you were going to graph this one in polar, you're 4 units away from the origin on the angle 0. So you're going to be over here. In fact, actually, you end up being at the x-coordinate 4 and the y-coordinate 0. It ends up being, it looks like the same number. It is the same numbers, but remember, here the 4 represents the radius and the 0 represents the angle. Here the 4 represents the x-coordinate and the 0 represents the y-coordinate. For B, we would go on the angle pi this way, but because it's a negative 3, we're actually going to go in the opposite direction. This point ends up being right here, 3 units on the x and 0 units on the y. So that ends up being our answer. For the last one, we're going to have to go back and use our formulas. So x is r cosine theta, which is 5 cosine pi over 8. And when we do it, we get about 4.619. Y is our sine theta, which is 5 sine pi over 8. Y is about, oh, that's a crummy about, but we're going to go with that. Sine pi over 8, 1.913. So the coordinates are 4.619, 1.913. And there you go. And these same formulas would have worked over here. It was just a lot easier not to use the formulas. All right, so that's converting. So now let's do something we haven't done yet. It's not that hard. I just have these two things. These two examples is really all we're going to look at. So describe the shaded sector using the inequalities in r and theta. And we've done area between curves before, and this is where we're going with this. Next section, we're going to be talking about this when we start doing the calculus of polar curves. So we're going to be playing around with areas of regions a little bit. And so understanding the inequalities in r and theta is going to help us out here. So think about what it might be. We'll do one together, and then I'll let you know, if you want, pause the video before we do B. All right, so let's look at A. As far as r goes, we are shaded between r equals 2 and r equals 4. Everywhere is shaded between those two. So that's all it wants, is 2 is less than or equal to r is less than or equal to 4. And then think about the theta. So if we're going around, because you always want to start from the smaller values going larger, so that means going counterclockwise. So we're starting at pi over 6 and shading to 2 pi over 3. It's really all we want. Pi over 6 is less than or equal to theta is less than or equal to 2 pi over 3. That's it. So think about what the inequalities would be for B. And if you were thinking 0 is less than or equal to r is less than or equal to 4, and 5 pi over 3 is less than or equal to theta is less than or equal to pi over 6, you'd be partially right. So your r would be good. We are going from 0 to 4 as far as the distance from the origin goes. This would not be correct, because remember what I said over here. You want to go from the smallest to the biggest. 5 pi over 3 is bigger than pi over 6. This inequality doesn't even make any sense. So what you want to do, where's my eraser? There it is. So think about what the equivalent angle would be in the negative direction. And so this is negative pi over 6. So if we start at negative pi over 3. If we start at negative pi over 3, we increase to 0 to positive pi over 6. That would work. Negative pi over 3 is less than or equal to theta is less than or equal to pi over 6. So just be careful. Make sure that you always go from the smallest to the biggest, and also make sure that you're not going around too many times in the circle. Don't say that it's like negative pi over 3 to 13 pi over 6, because that would be going around the circle once and then stopping there. So just be careful with those things. So that's all there is to that. Okay, so now what about this? Converting equations from rectangular to polar and back. So let's take a look at these. Now again, if you want to pause the video and try this on your own and then come back together, that's totally fine. I would encourage you guys to do that, to pause the video, see what you can get on your own, and then we'll meet back up. But we are about to do it together. I'm going to make this a little smaller. Okay, so r equals 2 sine theta. So remember, we have those formulas. These formulas right here, these are what's going to help us go back and forth when we're converting equations. So we're trying to go to rectangular. If I were to take this one and multiply both sides by r, it ended up helping a lot, because we know r squared is x squared plus y squared using those formulas. And we also know that r sine theta is y. There we go. Technically, we're in rectangular. Now, honestly, if you can get to this point, that's good enough. But let's see if we can remind ourselves what this is going to be. If you remember your conics, you can see that this is actually going to be a circle. I don't know how much you guys have actually done with conics, but when your x and your y are both squared and they have the same coefficient, it's a circle. And we can see it by completing the square. So if I go ahead and we'll have x squared plus y squared plus 2y. Oops, that should be minus 2y if I move it over. And then right now that leaves me with 0 on the right. But then complete the square by adding 1. So I'd have to add 1 over to this side. So, oh, I don't have my color again. Oh well, we'll go with this. So then we can see that it's going to be x squared plus y minus 1 squared equals 1. And there it is. There's our equation. So that's the first one. So that was a nice easy trick. So now let's think about b. What would that one be? I'm going to go back and try to get my pink back. All right. I want to do something kind of like this. It won't be exactly the same, but if I multiply both sides by this denominator, it gives me something kind of like it. I'll have r2 minus cosine theta equals 1. If I distribute, then I get 2r minus r cosine theta equals 1. So I can see the r cosine theta. That's nice. Now over here, let's see. I know that r is the square root of x squared plus y squared, and then r cosine theta is x, and now I'm good. I have it all in terms of x and y. But again, let's play around with this and see what we can get. I'm going to move the x over to the other side, and then if we square both sides, I get this. And then if I distribute, and then I'll collect all my x's on one side. So I'm going to have, whoops, not that. I'm going to have 3x squared minus 2x plus 4y squared equals 1. And if you take a look at this, again, I don't know how much you remember about conics, but when you have x squared and y squared, but the coefficients are different, but they have the same sign. So they're both positive, but they're different. This is an ellipse. So let's see what happens when we complete the square. I'm going to come up here. I'm going to have to factor out a 3. So that gives me x squared minus 2/3 x. And then 4y squared equals 1. So I'm going to complete the square by taking half of this and squaring it. So half of that is 1/3, negative 1/3. Square it, and you get positive 1/9. But if I add something to one side, I have to add it to the other. Now remember though, I haven't really added a 1/9. I've added 3 times 1/9, which would be 1/3. So I'd have to add a 1/3 onto this side. And so then that leaves me with 3 times x minus 1/3 squared plus 4y squared equals 4/3. And then if I multiply both sides by 3/4, again, I'm trying to remember to turn this into a 1 when you're going to write an ellipse in standard form. You want that right-hand side, the right-hand side to be a 1. So I'm going to wind up with 9/4 times x minus 1/3 squared plus 3y squared equals 1. Or I could think of it as x minus 1/3 squared over 4/9 plus y squared over 1/3 equals 1. Oof. Now I know that was a lot. Bottom line, if you can get to this line right here, if you can eliminate the r and the theta and put it all in terms of x and y, honestly, it's good enough. This is just for fun, practicing our conics. All right, let's take a look at these last two. What do we do with those? Well, these are easier because they're in terms of x and y to begin with, and think about what we got. We know x is r cosine theta, and we know that y is r sine theta. So r squared cosine theta sine theta equals 1, and you're done. Now, a lot of times we try to solve for r if we can. If I just move those to the other side, I can get that, and that's good enough. I mean, honestly, at this point, again, once you get it in terms of just r's and thetas, you get rid of the x and the y. That's really all I care about. Just another way to write it. So then if we do the same kind of thing with y equals -2, y is r sine theta. And if we divide both sides by sine, we get r equals -2 cosecant theta. Boom, done. So it's much easier to go from rectangular to polar. Polar to rectangular, you got to play around with a little bit. So there's that. All right. Now we're going to get really fun. Sketching a graph in polar form. So this part we haven't looked at all. So let's see what happens here. Now there are some polar graphs that just through use you'll get comfortable with. Honestly, for us in calculus, the good news is you're not really going to have to know how to sketch, but it really does help with some of the stuff that we're going to do with calculus if you understand how the graph is actually formed. And it really comes in when you're finding your limits of integration. So it's still a good practice to go through this. But don't worry, you're not going to have to actually create a graph from scratch on your own in this course. So this is just kind of your preview for it. So one way to do this is to make a table of values. So I've kind of set it up already. I've started it off. So let's make a table of values here. Let's see what this gives us. Now, personally, like when I do have to graph something from scratch like this, I like to use the angles that we're familiar with, but sometimes you do have to find values in between. Sometimes you're going to find this isn't enough, so I like to leave little gaps to fill it in, because the order, and you're going to see in a moment, the order that the points come in will really be important to be able to keep track of. So let's see what happens here. Let's go back to this blue. Okay, when theta is 0, plug it in here. So cosine of 0 is 1. 1 times 2 is 2. Pi over 6. When theta is pi over 6, 3 times pi over 6 is pi over 2. Cosine of pi over 2 is 0. Times 2 is 0. All right. If we have pi over 3, that's going to be pi. Cosine of pi is -1. We're at -2. When theta is pi over 2, we have 3 pi over 2. Cosine of 3 pi over 2 is 0. We're back at 0. This does not seem to be very interesting. 2 pi over 3, we got cosine of 2 pi, which is 1. 1 times 2 is 2. Sure looks like these points are bouncing back and forth between these. Okay, well, let's see what this gave us. So now I'm going to plot these points. So we're going to go on the circle with a radius of 2, angle is theta. Circle with a radius of 2, angle is theta, which in this case is 0. So that's this point right here. All right. Pi over 6, 0. Anytime you got a radius of 6, I mean, we're on this ray, but the radius is 0. We're just back at the origin. That's not very interesting. All right. Pi over 3, -2. So we're on the ray pi over 3, but because of the -2, we're going backwards. So we wind up right here. Then pi over 2, 0. Again, it's a radius of 0 puts us back at the origin. 2 pi over 3, 2. Oops. So here's 2 pi over 3, radius of 2, we're right there. 5 pi over 6, radius of 0 puts us back at the origin. And then finally on the ray pi, but we're going -2, so we're back here where we started. We have 4 points. We started here to the origin, down here, back to the origin, up here, back to the origin, and then back here again. Here, origin, down here, origin, up here, origin. It sure seems like we're just kind of tracing this, but it really doesn't make sense to have these sharp turns. It's probably doing some sort of circling around, but how is it doing it? We're going to need some points in the middle. Let's find out what's going on. So if I think about these points, pi over 6, that's the same thing as 2 pi over 12. Pi over 3, that's the same thing as 4 pi over 12. Pi over 2 is 6 pi over 12, and so on. I'm going to pick values in between, and so it looks like we could do pi over 12, 3 pi over 12, 5 pi over 12, 7 pi over 12, and so on. See what happens there. So I'm going to find these values. Let's do this in a different color. Let's use red. So pi over 12. So 3 times pi over 12, that's pi over 4. Cosine of pi over 4 is root 2 over 2, times 2 is just root 2. And let's go ahead and plot these points while we've got them. So pi over 12, root 2. Root 2, remember, is about 1.4. So if I go in between but 1.4, it's going to go somewhere there. Okay, so then we have in between here is 3 pi over 12. 3 pi over 12 times 3 is 3 pi over 4. Cosine of 3 pi over 4 is negative root 2 over 2 times 2 is negative root 2. So where does that point go? So here's the ray, 3 pi over 12. But because of the negative root 2, we're going to go in the opposite direction. So it's going to wind up around there. All right. Then we have 5 pi over 12. And 3 times 5 pi over 12 is 5 pi over 4. Cosine of 5 pi over 4 is negative root 2 over 2. Times 2 is still negative root 2 over 2. So 5 pi over 12 is this ray right here. But again, we're going to go in the negative direction. So we're going to wind up right about there. And then I'm just going to keep going. We got 7 pi over 12. That would be 7 pi over 4. That'd be positive, so it's going to be positive root 2. 7 pi over 12 is going to be right there. Then we have 9 pi over 12. Excuse me. And so that's going to be 9 pi over 4, which is coterminal to pi over 4. That's also going to be a positive root 2. Looks like we have a nice pattern where it's going positive, negative, negative, positive, positive. The next one's probably going to be negative. Well, we'll figure it out anyway. 9 pi over 12, like I said, is coterminal to pi over 4. We actually wind up right there again. Oh, 9 pi over 12, my bad. I'm thinking of something else. 9 pi over 12, we're right here, so we're right there. Okay, last one, 11 pi over 12. And 11 pi over 12 is times 3 is going to be 11 pi over 4, which is coterminal to 3 pi over 4, where cosine's negative that. It's going to be a negative root 2. 11 pi over 12 is here, but we're going in the negative direction, so we wind up right here. All right, we have some nice points. This all turned out to be very symmetrical, but what does this mean? So this is where the order is going to help us. I'm going to label these points A, B, C, D, E, F, G, H, I, J, K. Oh my goodness. And let's go ahead and plot these points here. So A is at 0, 2. This was right here. And then B went to here. C put us back at the origin. I'm going to wind up with a lot of points at the origin. So it's going to get a little crowded over here, but that's point C. Point D put us right here. Point E put us right here. Point F. G put us back at the origin. H put us up here. I put us right there. J put us right there. K put us back at the origin. And then L, 11 pi over 12. L put us right here. And then finally M put us right back here. If we follow those points now in order, we're going to see this. Starting at A, we go to B, to C, to D, E, F, G, H, I, J, K, L, M. And then it's just going to repeat. It ends up making a nice pretty rose. Starting at A, B, C, D, E, F, G, H, I, J, K, L, M. And there it is. So you can see that the order matters. Because sometimes, and this is just a little preview of what we're going to do, sometimes you want to know just the area of one petal. So just food for thought, because we will come back to this idea. Now these are all symmetrical, so you could find the area of any one of the petals if you wanted to know the area of a petal. But what angle, just like here, to find the area, we started at one angle and went to another? I wonder what angle we would have to start at and then stop at to complete one petal. So like I said, food for thought, but we will come back to that when we do the next section. Okay, we made it through the tough part of the lesson. This was the tough part, and also kind of the tedious part, as you could see. Thank goodness you don't have to sketch those on your own. Now just a quick look at some common graphs, and then that's the end of the lesson. So it's good to know circles that are centered at the origin with a given radius. So something like this, it's centered at the origin with a radius of 2. Well, it's always going to look like, in this case, it's r equals 2. Every point on this curve has a radius of 2, so we can just say r equals 2 and be done with it. So it's just simply r equals whatever the radius is. Now, it does get a little trickier if you're trying to think about circles centered at either A0 or 0A with a radius of A. So for instance, like right here, it's centered, this circle is centered at 2, 0, but it does have a radius of 2. So the x-coordinate matches the radius. It's going to hit the origin. So what is this one going to be? And then likewise, we have something similar over here. It's just the center is on the y-axis instead, but its center is at 0, 1. The y-coordinate matches the radius, so it hits the origin. So what would these be? So one of them is going to be r equals to a sine theta. That looks really messy. And one of them is going to be r equals 2a cosine theta. So can you figure out which one is which? All right, well, let's try to figure it out together. So think about going around the circle, and with this one, let's see if we can just use the angles 0, pi over 2, pi, 3 pi over 2. So when we're at 0, the sine of 0 is 0, we would be at the origin. Okay. When we here, if the angle is 0, cosine of 0 is 1. I'm going to look at this circle with a radius of 2. So 2a would be 2. This should be 4. So, oh, well, that's also on the circle, huh? But that wouldn't be over here, would it? Yeah, it does look like this is the one, whoops, that is r equals 2a cosine theta. This is r equals 2a sine theta. And again, you can make a table of values to figure it out. If you want to describe a line through an origin with a given slope, and we can see that with this guy, we can easily make a right triangle. So we can see that tan theta is going to be the y over the x, which happens to be the slope, whatever the slope is. Now, if I just give this a little subscript, so we'll say tan theta sub 0 is equal to 2/3, then I can solve for that angle and say it's tan inverse of 2/3, and so theta equals that. This is going to be the line. Any point that is on this ray, and you may be going, well, that only covers half of it. What about the other part? Remember, these just have negative radius, but we'd still consider them there. So we're covered. This covers the entire line in both directions because r could be positive or negative. And that describes every point on there because every point here makes the same angle with the x-axis. So those are just some good ones to know. And horrible news, that's the end of this video. So I'll see you in class. Have fun with the homework. Bye.